Now that we know how to calculate the non-standard voltage, we can talk about this special situation of a concentration cell, which is a voltaic cell where both the anode and the cathode have exactly the same electrode, but the concentration of the ions in the two different compartments is different. Okay, so electrodes are identical, but then just different concentration in the two compartments. Okay, and the reason there's a voltage here is because of the following. So if you look at your Nernst equation, which is this one right here, if you have the same electrode on the anode and the cathode, your E naught would be 0 volts, right? Because there's not going to be any difference because you're oxidizing in one and then reducing in the other one, but it's the same component. But then it's this part of the cell that's going to actually generate the voltage. So you might think like, why do we need something like this? Where's the advantage? Actually, there's a lot of applications for this. One of the ones that I'll talk in a little bit more detail is the pH meter. Okay, so we'll talk more about that later. Let's take a look first at how to calculate voltages for these concentration cells. So the simple way is, again, using this Nernst equation, understanding that the E naught here is going to be 0, so then the voltage comes directly just from this negative RT over NF ln Q component of that equation. And again, that could be written as negative 0.0592 over N log of Q. So this would be the actual voltage that comes from the concentration cell. Okay, we're going to take a look at an example here. So consider the following voltaic cell with both sides having nickel as the electrodes. One compartment, the nickel 2 plus is 1 molar, while in the other compartment we have 0.1 molar. So there's two questions here. The first one is determine which compartment is the anode, which one is the cathode, calculate the voltage generated. Okay, let's think about that a little bit. Okay, so we have both of these as nickel, so the reaction itself looks something like this. Nickel solid goes to nickel 2 plus, plus 2 electron, that will be the oxidation. The reduction is exactly the opposite of that, right? So again, this is the reason why if you calculate the E standard, whatever this number is, this number will be the negative of that, right? So if you can look up your values here, but one of them would be positive, the other one would be negative, and then when you add the two of them together, you get exactly 0 because the value of the two is exactly the same, because you're just reversing one reaction to the other one. That's why I kept saying earlier that the E naught would be 0 here. But because the concentration is different, this part of the Nernst equation will generate some kind of voltage. The question is, who's going to be the anode and who's going to be the cathode? That's question number one. Well, if you think about it, the site that has a higher concentration of nickel, so there is one site with 1 molar, the other one is 0.1 molar. The site with higher concentration of nickel, that means it has more plus, right? Plus site with less concentration of nickel, that has fewer pluses. So let's just put a couple. Okay, so which way is the electron going to flow? Well, the side that has more pluses is going to attract the electrons. It's going to attract the negative charge. So the flow of the electron is going to go that way. So therefore, the lower concentration is my anode and the higher concentration of nickel is my cathode. Okay, so that means that is how I'm going to write my equation. So I still have my equation here written on the top, but I'm going to make it a point to write down that this side, this is the oxidation, this is my anode. In my anode, and this is my cathode. In my anode, the concentration of the nickel is 0.1 molar. Okay. In my cathode, the concentration of my nickel is 1 molar. The reason why that matters is because when we do the calculation, the voltage comes only for the Q. So you need to know what is the ratio of products over reactant. You need to know which concentration is the product, which concentration is the reactant. So in this case, if I add these reactions together, okay, if I add these two reactions together, right, I get nickel 2 plus goes to nickel 2 plus, right? So if you write it that way, you don't difference, but in mind that the nickel 2 plus on this side is the 1 molar. The nickel 2 plus on this side is the 0.1 molar. So this is just a rewriting of this top equation here that I've written on the top. I just typed it here at the bottom. Okay, so that tells me that my product nickel concentration is 0.1 molar. My reactant nickel concentration is 1 molar. So if I want to calculate voltage, which is E, it's just going to be negative 0.0592 over N log of Q. Now I can plug in some numbers. The N here is because there's 2 electrons being passed around. Log of Q. Now I know my Q is going to be my product nickel, 0.1 molar, and my reactant nickel, which is 1 molar. So if I work that calculation out, I end up getting 0.096 volt. Okay, so I get some amount of voltage out of this concentration cell. Again, even though it's the same components on both the cathode and the anode. Okay, so you can see that it still generates a voltage. Now, as I said earlier, one application of a concentration cell is in the design of a pH electrode, right? How to measure your pH meters, which you've used in the lab before. So a pH meter is basically, if you recall what it looks something like this. It has this glass electrode, but inside that glass electrode, there's actually tubes of electrodes that are being designed in there. So one of them is called a reference electrode. The reference electrode basically has a solution that is always standardized, and it's usually a KCl solution. And this is maintained at pH 7. So this is just a split of those two electrodes being shown on the picture on the left here. So in the actual pH meter that you use, usually you just see one, but in one, that glass electrode, both of these pieces of electrodes that are inserted in there. So that small one is your KCl. So that one has a pH of 7. The concentration of H plus is always 10 to the minus 7. And then this other one right here is the one that you use to measure the H plus concentration in your solution. So let's say you have a beaker, okay? This is your solution. You insert that pH meter in, and you have a different H plus concentration right here. Let's say it's 10 to the minus 5. Because there's a difference in these two values of H plus concentration, that would generate a volt. That voltage is going to be calculated the same exact way as the way we just calculated it for that nickel concentration cell, right? So the voltage obviously relates to the ratio of these two concentrations. So if I know one of them is 10 to the minus 7, I can immediately calculate what's the missing one. Hopefully you see how that application of a concentration cell into the pH meter is pretty straightforward, right, in terms of the idea of it, because we just did the same type of calculation with a nickel. So in theory, we could design a nickel meter, for example, if we're interested in figuring how much nickel is present, how much nickel ion is present in a solution. And we can do this for all kinds of ions. Honestly, if you want to detect contamination in your water, you want to know how much mercury is in there, how much silver is in there, you can use a meter that's designed specifically for that ion using the concept of concentration cell. The other situation where concentration cell is really applicable is in biological systems. So in biological systems, you a lot of times have a cell or a compartment where you have the same ions both on the inside and the outside. So for example, you have sodium ion on the inside and sodium ion on the outside. And it turns out that the gradient or the difference in the concentration between those two ions generate a voltage, as we just discussed with the concentration cell. And that voltage causes the cell to do certain things. Okay, sometimes it causes the cell to open up, sometimes it causes the cell to shut down. So there's certain biological actions that happen depending on what kind of voltage is being generated. And this is how people have studied nerve cells or neurons for a long time using the idea of concentration cells. Let's take a look at one more example on how to apply this idea of concentration cell to calculate voltage. So in this example, we have a cell where we have a chlorine and chloride reaction. So in this case, one of the chloride has half a molar concentration of the chloride ion, and then the other one is 0.1 molar of the chloride ion. The question here is, what is the E cell of the reaction? And so same idea like the previous question with that nickel cell, you're going to first have to figure out which compartment is the anode, which one is the cathode, meaning that where is the electron flowing out from and what concentration of chloride ion each compartment. So I drew the compartments here just as a standard drawing, and we can think through a little bit about it. So again, if we want this side to be anode and we want this side to be cathode, that means we want electron to flow out from the left to the right. Now we know that electrons are avoiding the negative charge and going towards the more positive side. So since we're dealing with anions in this case, this side must be the half a molar chloride because it has more negative charge, which pushing the electron out. And this side is the smaller chloride concentration, thereby less negative, allowing the electrons to go there. So that's the way you want to think about it conceptually. You can then use that arrangement, now that you know that that's the anode, the other side is the cathode, you can use that to complete your reaction. So remember that the reaction itself is basically the same reaction, but just flipped, right? So the top one right here is the reduction reaction. This number here I just got from the standard reduction potential table, plus 1.358 volt for the reduction of chlorine gas to 2 chloride ion. And then for the oxidation, it's just the flip of that. The voltage is exactly the opposite. So then when you add the two together, you get an E naught that's 0, okay, which we know that always is the case for all types of concentration cells. So then the voltage will just come from this part of the equation, which again, I can now plug in some numbers here. I know that in this case, the chloride on this side, this is for the cathode side, is 0.1 molar. And then for the anode side, that's 0.5 molar. So this side is my reactant, this side is my product. So that's why when I do my Q, which is products over reactant, the value for the product concentration of chloride is 0.1 and the value for the reactant concentration of chloride is 0.5. And they both need to be squared here, as you can see, because the coefficient is 2. Okay, so it's 0.1 squared over 0.5 squared. If you calculate this out, the negative will cancel out with the negative you generate from the log. It gives you a positive voltage. So in this case, again, our setup is such that we would get a positive voltage out of it.